is Francesco Borra. I am a postdoc in ENS CNRS in Paris, and I'm part of Work Package 4 of the NeuCHiP project. I am a physicist and I have a background in statistical mechanics and in neural networks. And my contribution to the NeuCHiP project is related to compiling, that is, the activity of encoding a certain program into the neural structure of a system. So the main idea of a NeuCHiP project is to build a chip in which we do not have silicon circuits or transistors, but we have cortical neurons instead. And we would like the chip to be able to perform certain tasks. For instance, we would like to interrogate the chip. So we may encode, for instance, a signal into an electrical stimulus with which we induce activity in certain neurons as a question, and we would like to read the answer from the activity of other neurons. And of course, we would like the system to be able to give the correct answer. Now, one of the main issues is that neurons which are grown in a culture are connected randomly, and therefore they have a limited applicability. And what we would like to do is neurons to have a custom connection structure which allows it to solve our specific task. And in order to do so, we may exploit plasticity, which is one of the main features of the biological neural systems. So plasticity is the fact that when a neural system is active, the connections are modified depending on the activities of the system. So for instance, if two neurons have a correlated activity, which means that they are mostly active at the same time, their connection will strengthen in time. This is one of the most basic mechanisms, called Hebbian rule, and is one of the mechanisms which contribute to learning in the brain and to consolidation and formation of memories. And the idea is that we can design a training protocol that is a sequence of stimuli which will induce a sequence of activities, states in our chip. And depending on the activity states, we would like bad connections for our tasks to weaken in time and good connections to strengthen in time. And therefore, in order to do so, one has to have a good and theoretical understanding, a good modeling of how the system works. And of course, one has then to apply. And this mixture of theory and application is what I find particularly interesting in this project. In a broader context, this project belongs to the ongoing scientific activity revolving around understanding and controlling neural systems, whether in vivo, in the brain, or in artificial cultures as the NeuCHiP itself. And I think this is one of the great scientific challenges of our times, and since which hopefully will deliver useful technologies. And moreover, since we're dealing, after all, with the basic constituents of our brain, this kind of research also stimulates interesting philosophical questions and, of course, some potential ethical concerns as these neural technologies advance. So thank you for your attention.